So, now I will explain the first order derivative function. So, this in this experiment, in this block, I'm storing the y derivative function as a new variable which will store all the values of yi at first. So, like if this is our yi, then we will first replicate y derivative of I to be exactly like y of I, and then for calculating the y of I, we we will we will say this is our y of I and this is our new yt of I. Then we will first duplicate this. Now these two arrays have the same element. Now we will calculate the difference of the elements, this minus this, and put it here, this minus this and put it here, this minus this and put it here. So yt minus yt of I minus yt I minus 1 calculates the difference, and y of I equal to this equation just puts this to the difference in the above array. And this is the copying expression, and this is for the placement of the variable, of placement of the elements in the yth element, for which on which we have performed the signal processing of derivative. Now now we can observe the derivative signals, the obtained now we can observe the signals obtained after we perform the derivative operation. So, as we can see in this signal, this is the signal obtained after we perform the derivative block, after we uh, after we after we compile the so this that was the output after we get after we compile the compile and plot the derivative of the function. So now moving forward, uh, now we have done now we have done the derivative, first order derivative operation. Now we will calculate the moving average filter operation once again over the first order derivative operation, so that we were able to further reduce the noise, high frequency noise. This can be visible from this graph. See how the high frequency noises are removed, and also we can see uh, that we are able to calculate the derivative of the above of the blue function over in the red function or graph. So now I'll be moving to the next part of the code, and that is to calculate to detect where the peak happens. So which I named as peak detect. So here's the peak detect part of the code. So here we are first we are first we define in count function I, and I equal to 0 up to 150, and then when we to calculate the peak detect, first we take all the values of yi. If yi if less than equal to 0, then we put y of y equal to 0. So basically all negative values would be summed to 0. So sum would be taken as 0. Now moving on, in flag equal to 0 would be our flag counter, and sum equal to 0 would be our sum counter. This would be useful when we would be calculating the threshold value. Now moving on, for int I equal to this, this is basic definition of the to observe the maxima y, which says that y ith element is greater than both the I minus 1th element and I plus 1th element. And also I have used this y of I is greater than 0.001 to negate the effect of the small maximas, that small maximas or irregular maximas that will come. Now we as we move on now, uh, else so here we will just take if yi is if y if this it is greater than 0, then we will put it as yi, else we will put it to 0, and then we will calculate the threshold at sum equal to sum by flag, where sum is uh, the the peak value. So here the sum is sum is counted for each peak, the amplitude of each peak, and flag is the number of peaks. So we will calculate the threshold as sum of all the peak values and divide by the number of the times the peak occurs, and then y we will set the yi equal to 10 times of yi, so as to detect the peak more accurately. Here in this graph, this is the peak, these are all the peaks that we get. Now moving on, I would be calculating the distance. So distance between two values of the peak would be calculated as in this code what I'm trying to say is uh, um, the for each element, if for each element first I'll get this element, say I'll get this peak, and then the next time this peak occurs, my the yi value would be changed from 0 to some other value, so I would be able to identify the ith element between and for which we are getting the peaks. So now moving on towards the code. So this is the distance part. So these are the flag and distance is the difference between the elements for which we are getting the peaks. So here we have done for int I, once again we run the code for 150 elements, and if yi is greater than 0, we start the element, we start our counter, and it will move up till yi is again greater than 0, and then we will increase our flag. So basically distance would be I minus the start value. So if we are moving with I, some I will come, and then this I would be greater than 0, so our start would be set at here. Then each time start would be incremented as I would be incremented, I increasing up till here. Then as this comes greater than 0, our start would again be set to 0, and distance will be calculated as this distance. So so this is that code. And now to calculate the beats, as we are taking a signal of 50 hertz, so this is our signal distance equal to distance divided by 50. This is our effective signal, and in beats per second. So this would give us beats per second. Now to calculate the beats per minute, beats per minute, we multiply it by the signal by 60. So now I'll be running the whole of the code to monitor what's going on. So let me remove these comments. Now we will upload the code. So now we'll observe the values in serial monitor. So okay, let me see once. So we will comment this section, as we don't want our values to run to infinite. So we are able to get what the beat rate is. So as we are getting 73.8 as the distance, so this is the beat rate. 3 is the number of peaks, and 123 is the distance, the ith element distance. So here I conclude my demo. Thank you.